Please put your name in chat. Huh. Can y'all hear me?
Yes.
Well, I did hear you. Let's see. Try again. Can you hear me? Well, evidently I can't hear you. I did not say hello, buddy. All right. Someone talk to me again? I need to be sure I can hear you if someone asks me a question, so.
We can hear you.
Stupid machine has been farting up with me. Okay, try again.
Can you hear me? We can hear
Yeah,
you.
I can. All right. I just can't hear you on the. There's speakers in the room that I'm supposed to be able to hear you on, but it won't let me do that. And it changed my. All right. There we go. Now, where did we leave off? Were we doing polynomial functions last time, or?
Yes.
So how far into the polynomials were we, or did we just begin?
We were just beginning. We were in the definition of a polynomial.
So we talked about what a polynomial function is,
Yes.
what it looks like. Did we determine did we go through these three polynomial functions and identify it as a polynomial or not, and what the leading term is?
Functions.
I didn't hear you if you said something. I saw that you spoke.
Yes, we did.
Okay. So we did all of those. If you haven't put your name in chat, put your name in chat. Please pin my screen. Because then you can see much better what I'm writing. And then you click to maximize the Zoom window. Oh, we talked about this not being a polynomial function, it's just a, it's a ratio of two polynomial functions. And constant is a polynomial function. It's a non-zero constant polynomial function. The leading coefficient and the constant term are both 9. And this too is a polynomial function. It's a 4th degree polynomial function where the leading term is a negative x to the 4th power and the constant is 0. Because it's easier to answer these questions if we multiply this all out. All right, there's no constant, but we're always adding 0, so the constant is 0. Make sure you signed into chat. Make sure you pin my screen. And I prefer that you all be on screen, but that's not going to happen. Nobody does that for me anymore. Okay. Did we go over this chart?
No.
No? Okay. I talk about why the 0 function has no degree. All right, this is the 0 function, f of x equal to 0. We talk about the degree. The degree of a function is the highest exponent on the variable. So x times x is 0. 0 times x to the 4th power is 0. 0 times x to the 200th degree is 0. 0 times x to the 2364th degree is 0. By this reckoning, 0 can have any degree. Well, that's not possible. So we say it has no degree. Because what degree are we going to call it? I mean, I could even have negative exponents on x. I could have fraction exponents on x. So the 0 function has no degree. And its graph is the x-axis. All right, so this is the equation for the x-axis. Y equals 0. All right. We say a constant function has degree 0. That's why it's a sub naught. Because if I have some number a sub naught and I multiply it by x to the 0 power, remember we're always multiplying by 1. And 1, I can use a multiple of things for 1. I can use x to the 0 power is 1.
Sir, the screen looks kind of blurry.
Say again?
The screen looks blurry, so we can't really read what the table says.
Jeez Louise. that a little better? Not much, is it?
Actually, I think it's the same.
Huh?
I think it's the same thing.
Yeah.
The other class was pretty good sometimes, but like when you reconnect again, sometimes it get blurry again. But I think it's, I don't know, maybe it's the reconnection or something like that.
Well, yeah, I mean, it should focus in.
Actually, I can only read the paragraphs on the top.
Yeah,
Okay. That was it.
okay. Let me see. Okay. Well, let me try something real quick. And this camera has no presets in it, so that's another bugaboo I have with the IT department about this. And that's no better, right?
Yeah, no.
Yeah, it's the same thing. Okay. So then this here is f of x equals a sub naught, where a sub naught is not equal to 0, is a constant function. It's a horizontal line with the y-intercept being a sub naught. Another way of writing this is y equals a sub naught. And so it's a horizontal line, and this is the y value, a sub naught. So y equals 3, f of x equals 3 goes through 3 on the y-axis. And it's a horizontal line where all the y values are 3. So all the y values on this line are whatever a sub naught is. Linear function has the linear function y equals mx plus b, but they write it as f of x equals a sub 1x plus a sub naught, where the b is just the a sub naught and the slope is a sub 1. So this is writing it in polynomial function format, and this is writing it in slope-intercept format. It's the same equation. It's just the letters are just different notations for the same thing. The slope is m, the slope is a sub 1, the y-intercept is b, the y-intercept is a sub naught. And so that's what this is talking about over here. It's a non-vertical, non-horizontal line, so it doesn't go straight up and down or this way. So it's not those types of lines. So that means it's this kind of a line or this kind of a line. So we're talking about these types of lines, not horizontal or vertical. And where it crosses the y-intercept is a sub naught, and the slope is a sub 1. And the last one they talk about up here is the parabola, the quadratic function. Its graph looks like a parabola, and the graph is concave up if a sub 2 is positive, and it's concave down if a sub 2 is negative. So what that function looks like, a f of x equals a sub 2x squared plus a sub 1 x plus a sub naught. Where with a quadratic, you're used to seeing ax squared plus bx plus c, but we're using the polynomial notation here, where a is a sub 2, b is a sub 1, and c is a sub naught. All right, and the stipulation here is that a sub naught cannot be 0, and we already discussed why. All right, and this is a quadratic function. It's a parabola. If the leading coefficient is positive, then it's concave up. If the leading coefficient is negative, then it's concave down. This is just putting in an organized form what you should already know. Okay. And they're just using the polynomial function notation for the coefficients. All right. If you take a course in calculus, you will learn that the graph of every polynomial function is both smooth and continuous. By smooth, we mean it contains no sharp turns, no corners, no cusps, no gaps. Oh, okay. So that's for the smooth, and by continuous means there's no gaps or holes. It can be drawn without lifting your pencil from the paper. So this is not a polynomial function for several reasons. Two of which is that it's not smooth because of the corner and the cusp, and it has a gap and a hole, so it's not continuous. Where letter A can be the graph of a polynomial function because it's both smooth and continuous. This is what we call a power function. And a lot of times when we talk about power function, we say A is 1. But that's when we start talking about the parent function of other functions. So A is not 0. We always have that stipulation because if A is 0, then you don't have a power function, you have a 0 function. And n is greater than 0 and it's an integer. So n could be 1, 2, 3, 4, 5, 6, the counting numbers. Okay. The positive integers are the counting numbers. We also call them the natural numbers. That's why we typically use the letter n here, because we're talking about counting the natural numbers. Okay. So this is the standard form of the power function. It's a monomial, so there's only one term. And there we have it. Okay. Now, if it is a power function of an even degree, then that power function is an even function. So it's going to be this graph is going to be symmetric to the y-axis. The domain is all real numbers, and the range is a set of non-negative real numbers. So 0 to infinity. The graph will always contain these 3 points. -1, 1, 0, 0, and 1, 1. -1, 1, because -1 raised to any even power will be a positive 1. -1 squared. -1 to the 4th power, -1 to the 6th power, -1 to the 8th power, -1 to the 200th power. It's still going to be 1. Right? 0 to any power is going to be 0, and 1 to any power is going to be 1. So these 3 points will be on the graph of an even powered power function, or an even degree power function. And as the exponents increase, well, as the exponent increases, as n gets larger, all right, so you get a larger and larger even degree function, squared to the 4th, to the 6th, to the 8th, to the 9th, to the 10th. Then the outside of -1 and +1, the graph gets steeper. Okay, but in between -1 and 1, the graph tends to flatten out and look like it's getting closer. Well, it is getting closer to the x-axis, to the point where it looks like it is the x-axis. But the only time it is on the x-axis is when x is 0. And this is talking about in behaviors. As x goes to -infinity, the y values go up. And as x goes to +infinity, the y values go up. So this is telling me it's going up to the left and it's going up to the right. So when you have an even degree power function, then the end behaviors are both going up. So to the left it goes up, and to the right it goes up. I use the arrow notation. I used one textbook that this is how they described it. As x goes negative, y goes positive. You can use this here to describe, well, both of these. You can use both of these to describe that. Or you can say it goes up to the left and up to the right. So talking about end behaviors, there are several ways of stating it. But we're basically talking about what direction is it headed? Up or down? Now, if n is an odd number, so we have an odd degree function, then it's going to be symmetric with respect to the origin because it is an odd function. If I put -x in for x, I get a negative f of x. Okay? The domain, both the domain and range are the set of all real numbers. As with all polynomial functions, the domain is all real numbers. And because it's an odd degree function, its range is going to be the same. And the graph always contains these 3 points. It'll go through -1, 1. It'll go through 0, 0. And it'll go through 1, 1. 1 to any power is 1. 0 to any power is 0. -1 to an odd degree is still going to be -1. And this fits -1, and 1 fit with the fact that it's an odd function and symmetric with respect to the origin. Because with an odd function, you change the signs of both terms, of both x and y, you'll get another point that is on the graph. So if I change the signs here, I get that one. If I change the signs there, I get this one. And 0, 0 is just 0, 0. No matter what you do to it by multiplying. Okay. Now, just like with the even degree functions, as n increases, the steepness of the graph and the n behaviors gets steeper. So when we're talking about x cubed and jump to x5, then it's going to be a steeper curve. So the line's graphing will be a steeper. And then just like with an even function, when x is near the origin, the graph tends to flatten out. Now, with these functions, they'll look something like this, but it'll, as the n increases, it gets steeper on this side and comes closer to the x-axis in between, where this is -1, -1, and this is 1, 1, and it'll just keep getting steeper and steeper. And in between here, it looks like it's getting flatter. Well, it is getting flatter and flatter. It's just getting more and more horizontal until it looks like it actually is the x-axis, but it actually isn't. And the end behaviors talk about as x goes in the negative, y goes in the negative. And as x goes in the positive, y goes in the positive. Another way of looking at this is saying that the function comes out of negatives and goes into the positives. Where with even degree power functions, either they're both in the positive, going in the positive direction, provided a is positive, or yeah, well, we're dealing with a being 1. So now to graph using transformations. So the first thing to do here, we have f of x equals 1 minus x to the 7th power. First thing to do is to rewrite this as in standard form, which is what I would do and which the textbook does, because I just like to have it in standard form. So x to the 7th is my parent function. So the graph of x to the 7th looks something like this, or exactly like this. It'll go through the points -1, -1, 0, 0, and 1, 1. It'll come up very steeply, and then it'll flatten out here in the middle, and then go back up very steeply. Okay. Now, this negative sign here means I'm changing my y values of x to the 7th. So that means the sign on this y value here gets changed. So this -1, -1, the y value -1 becomes a positive 1. So this point here got moved up to here because I multiplied my y value by a -1. So multiplying this y value by a -1 gives me 1, -1. And 0, 0 doesn't change. So now you draw, so instead of going down to the left, now it's going up to the left. Instead of going up to the right, now it goes down to the right. And so this is our graph now. I just, where it was negative is now positive, and where it was positive is now negative. So that's what happened here. So we're done with these changes. Now we're looking at this change here, the +1. That's a vertical stretch. No, that's a vertical shift. So this means I'm adding 1 to all the y values. So I'm going to add 1 to +1, and it brings up to +2. I add 1 to this 0, and it brings it up to 1. And I add 1 to this -1, and it comes up to 0. And so now the whole entire graph got moved up 1 degree. 1 unit. And that's what this graph shows. Is it in my, barely in the view. Yeah, I'm gonna have to shoot off an email. Both to IT and to my department. It's better if I complain to my department head because she can get things done faster than I can. Okay. Where did I put? Now, here I have x to the 6th as the parent function. So that means the points 1, negative 1, 1, 0, 0, and 1, 1 are on that graph. And that's what we show here. This is the point negative 1, 1. I'm going to draw over this. That'll help show it up a little better. I don't know about you, but that squeaking is really getting to me. I hope that aids in it showing up a little better. Okay. Well, that's not what I wanted. Okay, if you pin my screen, it shows up a lot better than if you're just trying to see it from the regular Zoom view. Zoom view. Okay. Now, here we're changing our 0, 0. We're changing 0, 0 because we're changing what x value makes 0, 0. So I want to see where x plus 1 makes it 0, so that's x equals -1. So 0, 0 gets moved 1 unit to the left to -1, 0. And so that means I'm moving all these points to the left 1 unit. Oh, Thomas, keep forgetting to. So I'm subtracting 1 from -1, that gives me -2. I'm subtracting 1 from the x value 0 to give me a -1. And I'm subtracting 1 from the x value 1 to give me 0. So -1, 1 went to -2, 1, 0, 0 went to -1, 0, and 1, 1 went to 0, 1, and the graph moved accordingly. Okay, so we're done with the inside. Now with the only thing that's happening to the outside is times 1/2. We're not doing a vertical shift, we're just doing a vertical compression because A is less than 1, so that means we're going to be squashing it towards the x-axis. So each y value gets cut in half. So multiplying 1 by -1, multiplying the y value by 1/2 takes us to 1/2. Multiplying 0 by 1/2 stays at 0. And multiplying this 1 by 1/2 brings us down to 1/2. So up this y value would come down to 1/2 to 1. This y value would come down to 1.5. This y value would come down to 2. So it would end up looking something like, well, it'd still be coming down low. And so that's what the next slide does. All right, this -2, 1 became -2, 1/2. The -1, 0 stayed -1, 0 because multiplying 0 by anything didn't affect it. And 0, 1 became 0, 1/2, and then the graph got squished downwards appropriately. Questions? All right. Now, if a polynomial function f is factored completely, it's easy to locate the x-intercepts of the graph by solving the equation f of x equals 0. So you set the expression that's the function equal to 0, and you get an equation that equals 0, and you solve. And then you factor and use the zero product rule. Well, they say property, I say rule. All right, if you have a product that equals 0, then one of those factors, a product is multiplying factors together, and so one of these factors has to be 0. So A equals 0, B equals 0, C equals 0, or D equals 0. And so that's what we do here. Now, this picture actually goes with the next slide. Because once you find those zeros, you can look on either side of the intercepts and look at what the sign is. Okay, if the sign is different on either side of that x-intercept, okay, so it's below on one side and above on the other, it's below on one side, above on the other, it's below on one side, above on the other, then it just crosses the x-axis. And you can tell which direction because is it coming from the negative and going into the positive, or is it coming from the positive and going into the negative? And then to determine if it just touches there, if they're both below or they're both above, then it comes up and touches or comes down and touches, because on both sides it's both negative or both sides is both positive. So they're either both below or they're both above for it to touch there. And that's what the next slide is talking about. No, it isn't. They didn't explain this picture. I just did. Okay. And that's what's going on here. So now f is a function and r is a real number 0 for which f of r equals 0. Then r is called a real 0 of f. So for this particular thing, we're talking about r being the 0 of a polynomial function. Sometimes I use the letter c for being the 0 of a polynomial function. Well, not C. They use R. They use C for something else. As a consequence of this definition, the following statements are equivalent.
Sir,
What they mean by what?
your
I'm frozen.
We can't see your video anymore.
How about now? I didn't
Thank
say
you. Yes,
by
better.
now. I said, how about now? Stupid
Yes, we can see it.
Okay. So if one of these statements is true, all 4 of them are true. That's what this means by equivalent. If r is a real 0, then that means it's an x-intercept. Haven't I been saying that all along? Because these are talking about the same numbers in 2 different ways. One is where the graph hits the x-axis, and the other is making the function equal to 0. Okay. X minus r is a factor of f. That means whatever r is, that means x minus that number is a factor of the function. It's one of the and if r is, then it also means that r is a solution to the equation f of x equals 0. Well, we usually use this to find r, and that tells us it's a 0 of the function. And if it's a 0, it's an x-intercept, and if it's any one of these, it's x minus that number is a factor. So we can use this information to write equations if we're given the zeros of a function. So like on this, here, we're told what the zeros of a 3rd degree function are. All right, I have a 3rd degree function. That means I can have at most 3 zeros. Well, here I have 3 zeros. That means x minus a -1, which is x plus 1, is a factor. X minus 2 is a factor. And x minus 3 is a factor. So I multiply these 3 things together, x plus 1 times x minus 2 times x minus 3. That's the function factored. But I don't know what the leading coefficient is. All right, this is assuming the leading coefficient is 1. But I don't know what it is. So I'm going to put an a out here, a times this, and that gives me my function. A can be any real number except for 0. Because if it's 0, we don't have a polynomial function, we have a constant function. we have a zero function. So this is our function. And that's what they do. Now, to verify here, to verify this result, they're going to set A to 1. And we'll discuss why. So here they come up with the same three factors I did. All right. A minus a -1. We need to simplify this so we have A plus 1. And then x minus 2 and x minus 3. We multiply them all together and we tack an A here because we don't know what the leading coefficient is. Okay. Where A is a non-zero real number. Okay. Now, to graph it, the A value causes a stretch or a compression. So we're going to be pulling it either away from the x-axis or towards the x-axis, but that does not affect our zeros. Because it doesn't matter what I multiply by here, some number out here. If A is -1, it's still all going to equal 0. If x is 1. If x is 2, it doesn't matter what A is because I'm going to be multiplying by 0 and it's still 0. If x is 3, then I'm still going to get a 0 here, and multiplying anything by 0 is still going to give me 0. So the zeros will still be zeros no matter what the leading coefficient is. So that's why they're going to set A equal to 1, because that's easier to worry about when typing it into the calculator or using Desmos or some other online graphing feature. And they type it in exactly this way. They didn't have to multiply it all out to find out what the polynomial was. And there we have it. Now, if you want to experiment with this, which is something I would do, I would have this in as y sub 1, and then I'd put in a y sub 2, and I'd multiply in by different a's. So I would have A be 0.01 or 3 or -4. And I'd put in them all three of those just to see what the graph looks like compared to this one. And they all will go through these 3 points. The y-intercept will change because that'll change our constant on the end. And multiplying by a positive integer makes it stretch outward away from the x-axis. Multiplying by a negative integer does 2 things. It stretches away from the x-axis and flips it across the x-axis. So if I just multiply by -1, it would be the mirror image of this thing going like this. Okay. So it would look, and that's just doing a negative sign out in front. If I multiply by 0.01, then that's going to look something like this. What is that? 6.06. Oh, wow. So that's even less. So it's going to go through like that. That's where the coefficient is. The leading coefficient is 1/100. Oh, it's not even, it's just gonna. So that's A equal to 0.01. So that, yeah, playing around with it, you get some pretty interesting looking curves. And I put it over here. All right. And the x-intercepts will remain -1, 2, and 3. -1, 2, and 3. All right, real zero multiplicity M. If I understand what they're saying here. So basically, if you have x minus r raised to some power, and you have another x minus r to some other power, then you combine them to one term, x minus r to the two exponents being added. And that will be the largest exponent on x minus r you can get. And so that m is the multiplicity number. So r is a zero of multiplicity m. That means r shows up as a zero m number of times. So here, x to the third, that means we have x times x times x. X shows up 3 times as a factor. So that means 0, x to the third equals 0 means 0 is a 0 of the function, and it shows up as a 0 3 times. X minus 5, that has an exponent of 1, so it only shows up once as a factor, and so 5 will show up as a 0 exactly once. And x plus 1/4, plus 1/4, what happened to everybody? Why was it?
Your camera.
Yeah,
Turned
your
off.
camera went off again.
Okay. Zoom has really been messing with me today. Well, in this classroom. In the other classroom, it wasn't. X plus 1/4. So I have 1, 2, 3, 4 of these factors. So that means -1/4, which makes this 0, shows up 4 times as a 0. So it has a multiplicity of 4. Where 5 has a multiplicity of 1 and 0 has a multiplicity of 3. Okay, please notice there's only 1 6 out here because only the 3 is being multiplied. As the x is only being raised to the third power, not the 6 as well. Oh, damn it. So 0 is a real 0 of multiplicity 3 because the exponent on the x factor of the factor x is 3. 5 is a real 0 of multiplicity 1 because the exponent on x minus 5 is 1. And -4 is a real 0 of multiplicity 4 because the exponent on the factor x plus 1/4 is 4. Okie doke. Okie doke. Now the x and y intercepts. The y-intercept can be simply found by putting 0 in for x. So 0 minus 3 is a -3. -3 squared is 9. 0 plus 4 is 4. So this is 9 times 4, which is 36. So we have the point 0, 36. I'm just going to be listing points over here that we can graph. The x-intercepts, well, that's 3 and -4. So we have the point 30 and the point -40. So my y-intercept is the point 0, is 0, 36. My x-intercepts are 30 and -40. All right, so we look at this. So let me come down here to, let's see, 1, 2, 3, 4. 1, 2, 3, 4, 5. Go down to 5. So this is -5 and this is +5. So I have an intercept at -4 and I have an intercept at +3. So it divides my regions into 3 regions here. This region and this region and here, this intervals actually. So from -infinity to -4, -4 to 3, and 3 to +infinity. And so to do letter B, we pick values, x values, to find out where the graph is it above or below. So I'm going to use -5, and I'm going to use -2, and I'm going to use +5 for my values. So I'm going to find f of -5. So -5 minus 3 is a -8. -8 squared is 64. -5 plus 4 is a -1. 64 times -1 is a -64. So over here is below. Let me write it down here. Below. And that's the point -5, -64. Yeah, I'm going to erase those and move them a little bit. Okay. Now, in between -4 and +3, I'm going to look at what happens at -2. And so now I'm going to do f of -2. Right? So -2 minus 3 is a -5. -5 squared is 25. -2 plus 4 is a +2. So 25 times 2 is 50. So that's the point, -2, 50. And now I'm looking out here at +5. And so now I'm going to put positive, I'm going to find out what, all right, so in here, 50 is positive, so that means it's above in here. Well, I kind of already knew that because of the y-intercept. The y-intercept gave me that. But I wanted to find other points as well. Locate other points. And then I put +5 in, so I'm going to find out what f of 5 is. And so I'm not showing my work. I would expect you to show your work. I'm going to put 5 minus 3 squared times 5 plus 4 5 minus 3 is 2, 2 squared is 4, and 5 plus 4 is 9, so that's 4 times 9, which is 36. So when I put 5 in, I get 36. So the point 536 is on that graph. And 36 is positive, so that means it's above over here. Okay, it's below on this side of -4, and it's above on this side of -4, so that means it's going to be coming up like this. At 3, it's above on both sides, so that means it's going to come down and bounce back up. Now I put these other points down. All right. Notice my scale in my y direction is much larger. It's larger numbers, so I'm gonna shrink my scale down, and so I'm gonna have this up here be the y-intercept. So since that's at 36 and this is at 50, so 50 will be about here. All right. That means 64, negative 64 is going to be way down here somewhere. And that's just telling me it's dropping like a lead balloon over here. So I don't even need to put this point on the graph and just concerned about up here right now. And at 5, it's back up to 36, which is about here. And so it's going to come up to here, make a turn, and come down to here, and make a turn, and go up that way. Look, and then I could find other points other than the ones I found here. I could find I could plug in 4. If I put 4 in for x, I'll get 6. I've done this before so many times. I've memorized some of these. If I put -3 in, where is -3? Oh, -3 takes me up to 48. No, -1 takes me up to 48. And where does -3 go? -3 goes to 36. Oh, So at -3, it's at 36 again, and over here it's at -1, it's at 48. I don't know where 1 and 3 take us, but they're less than 36 and more than 6. That's all I know. Oh, well, 2 takes us up to 6. So we could graph more points, but these here are sufficient to graph the thing. And they do something very similar to what I did. And putting 0 in for x, you get 36 as the y-intercept. And the x-intercepts satisfy the equation equal to 0, so you set each of those equal to 0, and you find out that x is 3 or x is -4, so 3 and -4, which is what we determined these 3 points here the same way they did. And then looking at those intervals, you can find the intervals divide or the x-intercepts divide the graph into these three intervals, I just like to look at it as on the number line, rather than just writing the numbers there. And they kind of do both here. Here they have it on the number line where here's my x-intercepts, and here's the intervals we're talking about for this picture. And they picked a number in this interval, -5. They picked a number in this interval, -2. And they picked a number in this interval, which is 5. They could have chosen 4. They could have chosen 6. They could have chosen 10,000. But you want to pick something close to the x-intercept that shows you what's happening. And then they found those three values, the same three values I did, -64, 50, and 36. And then they talked about it below, above, and above in those particular intervals. And that tells you that it passes through -4 and it touches at +3. And then they wrote those 3 points like I did here. As soon as I found those values, I write down the points. I don't know. And they kind of did it same way. Okay. And so you plot the points, and that's what I did. I plotted 0, -4, 0. I plotted -2, 50. I plotted 0, 36. I plotted 3, 0. And 5, 36, and then sketch the graph. All right, -5, -64 won't fit on the graph they created, so they didn't worry about graphing. They could have put in that -3 took us to 36, which is that same point there, same y value as here and here, and then at 2 it's at 6, and at 1, they show it's going to be close to 20. I don't remember what it was. I don't remember putting 1 into the function. I know at -1, it took us up to 48. That means the local maximum is going to be just to the right of this point. Just to the right of -250. So that local maximum there is going to be around 51, 52. Let me see. If we were to multiply that out. Anyway, I'm not going to do that right now. So if f is a polynomial function of n degrees, then the graph has at most n-1 turning points. What do they mean by a turning point, you might ask? Here's a turning point. At a local maximum, we have a turning point. At a local minimum, we have a turning point. How many turning points? 2. What's the degree of this function? 3. What's 3 minus 1? 2. Oh, 2 turning points. The maximum, the most number of turning points it can have is n-1. Think of a linear graph, a line. How many turning points can a line have? None. It's a straight line. There's not going to be any turning points. What's 1 minus 1? Right? The degree of a linear function is 1. What's 1 minus 1? 0. Have 0 turning points. X squared. How many turning points does x squared have? X squared has 2.
1.
What was being said? I heard you. I just talked over you.
Oh, that the quadratic function has 1 turning point.
1 turning point. Or at most, but it will have 1 turning point, n-1. 2 minus 1. So a fourth degree at most will have 3 turning points. It could have just one. It won't have none. Okay. So if you know how many turning points a function that the graph has, then the smallest degree is one more than the number of turning points. So a fifth degree polynomial could have 2 turning points, could have only 2 turning points, because they're saying at most. So at most, a fifth degree polynomial could have 4 turning points. But it could have only 2, or it could have none. So which of the graphs on the next slide could be graph of a polynomial function? For those that could be a polynomial function, describe what the real zeros are and state the least degree. What's the smallest degree that polynomial function can have? So, is this a polynomial function? This is a definite yes or no.
No,
Why not?
because it has a gap.
It has a gap. So it's not a continuous graph. The graph has to be smooth and continuous. But because there's a graph, it is not continuous. I mean, it's not a polynomial function. Is this a polynomial function, or could it be a polynomial function?
Yes.
Yes, because it's a smooth curve. It's a smooth, continuous curve. What are the x-intercepts? What are the x-intercepts? Where does it cross the x-axis? All right, this is -5,
-3, 0,
-3,
-1, and 1.
-3, -1, and 1. What's the y-intercept?
-3.
-3. So it has a y-intercept of -3 and x-intercepts of -3, -1, and +1. What was the other? Oh, the number. What's the smallest degree this function could be? All right. How many turning points are there here?
2.
2. So we look at what's the smallest number n where n minus 1 is at least 2. So we solve for n, and that tells us the smallest degree.
3.
3. Just like the problem we just did. So what are they saying here? I gotta sit down for a second. Okay. The graph could be the graph of a polynomial function because the graph is smooth and continuous. It has 3 real zeros, -3, -1, and 1. They didn't ask for the y-intercept. The graph has 2 turning points, so the degree of the polynomial function must be at least 3. Is this the graph of a polynomial function? Yay or nay?
No,
Because
it has a corner or a short turn.
it has a corner sharp turn. Either way is acceptable. Has a corner at x equals 1. A graph of a polynomial function is smooth. So this is not smooth. Is this the graph? Could this be the graph of a polynomial function? Is the graph smooth and continuous?
Yes.
So yes. What are the x-intercepts?
Sorry, sir, I can see the numbers. I think it's 5, like even the.
Okay, yeah, it's -5 to +5.
I think -3 and the one that it's on the middle, like 0.
0. So -3 and 0 are the x-intercepts. And they're not asking for the y-intercept, but it's 0 as well.
They're 0, yeah.
How many turns?
3,
3. So what's the smallest degree?
4.
4. Okay. Now, what are they talking about here? Oh, in behavior. If you have a polynomial function, the end behavior will be the same as the graph of the power function of the leading term. The leading term determines what the end behavior is going to look like. Okay. And the end behavior depends upon 2 things. It depends upon the exponent, is it even or odd, and depends upon the leading coefficient, is it positive or negative. Now, I like to set this up a little differently. And I probably should go through and change this slide so it fits that. But it would be like if I took these 2 pictures and put it down below here. So where I talk about is in even or odd for the 2s. So I do it this way. So if n is even and n is odd, and then the 2 columns is a greater than 0 or is a less than 0, a sub n. So if it's even, then they're both going up if a is positive. If a is negative and n is even, then they're both going down. And that's what this is showing. As x goes negative, y goes positive. As x goes positive, y goes positive. As x goes negative, y goes negative. As x goes positive, y goes negative. That's what the f of x is, the y value. That's for when you're dealing with an even degree polynomial. When you're dealing with an odd degree polynomial, if a is positive, then you're going down to the left and up to the right. Going down to the left, up to the right. We're coming out of the negative and going into the positive. That's another way of looking at this. What are you coming from? What are you going to? I'm coming out of the negative and going to the positive. As x goes negative, y goes negative. As x goes to negative infinity, y goes to negative infinity. So as x goes to the left, y goes down. And over here, as X goes positive, Y goes positive. So I will ask you these questions on the test about when you're graphing these things. I will ask for end behaviors. How you tell me what the end behaviors are doing is entirely up to you. I like to use the arrows here. All right, to the left it's going up, and to the right it's going down. When n is odd and a is negative, it's going up to the left and down to the right. Or you could use those words. Goes up to the left, down to the right. It goes down to the left, down to the right. Or they're both going down. Both end behaviors are going down. Both end behaviors are going up. When n is odd, the end behaviors are going in the opposite directions, because it goes down to the left or up to the right, or it goes up to the left and down to the right. Dun, dun, dun. And so this is what we use, well, and it helps us in graphing, because once we know that, when we start trying to graph these things, then we know if we find this endpoint over here, and we know this is true, that it's an odd degree with a leading coefficient is negative, then that means this is the most left x-intercept, then it's going to go up this way. I know that. And whatever this x-intercept is over here, it's going to be going down that way. I know that from this. There might be another x-intercept or more in between, but I know at the ends that's what's happening. And that's going to help me graph. Do I need to find values over here for x and y? It'd be a good idea to do it just to see how severe that drop off is, or if it's this one, how severe it's growing or going down. I brought it with me. Okay. So now, here we have this function here. And we can determine, is this, which graph could be the graph of this function. The first thing I look at is the constant. Because what is the constant of any polynomial function? The constant is what? Somebody was walking by outside and they were looking at me like I was staring at them. I don't have anybody in here. Anyway, so this plus 3, what does that mean for the graph? What do I say the constant is? For any polynomial function, the constant is the what?
The y.
Yes. The y-intercept. So which of these fit that the y-intercept is positive? I don't even care about the fact that it's 3. It needs to be positive because it's a positive 3. Well, this could be a positive 3. This could be a positive 3. This could be a positive 3. And this one's gone. We can forget about A, because the y-intercept's on the wrong side of the x-axis. It's supposed to be up here, not down here. So we can forget A. Now everything else is determined by this puppy, the leading term. The degree is 5. So what's the maximum number of turning points it could have?
4.
4. The maximum number of turning points is 4. Huh. Is this 4 turning points? You know,
No.
1, 2, 3, 4, 5, 6, 7, 8. It's got 8 turning points. So no, there's no way this could be a degree 5. This has 1, 2, 3, 4 turning points. This one has 1, 2, 3, 4 turning points. So it's either going to be A or D. So boom, I eliminated another one. So now I'm going to look at end behaviors. All right, it's an odd degree function, so that means the end behaviors are going to go in opposite directions. All right, they're going to go in opposite directions. Is A positive or negative? Is the leading coefficient positive or negative?
Positive.
Positive, so that means it's going to come out of the negative and go to the positive. It's down to the left and up to the right. Is B or D down to the left and up to the right?
B.
B is. Goes down to the left and up to the right. This one is the reverse. So if it was a negative 5, negative x to the 5th power, then it would have been D, but it wasn't. It was positive, so it's B. Okay. So yeah, so they go about it the same way I did. They eliminate A, and then they look at the turn. Do they look for large values? Oh, they look at the end behavior first, where I looked at the end behavior last. If they look at the end behavior first, then we can yeah. We can't factor the thing because we don't know what B and C are. Oh yeah, all right. Then they all right. So now they moved on to the end behaviors, to the number of turns. So it has at most 4 turning points. C had 8 turning points, so they eliminated that one. I thought they were going to look at, oh, they did eliminate D because it did not have the right turning point. It did not have the end behaviors that were appropriate. So they first eliminated D and then eliminated C, where I eliminated C first and then eliminated D. In any case, we both wound up with B as being the correct graph. Find a polynomial whose graph is shown. Use the smallest degree possible. All right, we have those 4 statements that are always true. If R is a 0, then R is an x-intercept, and x minus R is a factor, and R is a solution to f of x equal to 0. Well, I have 3, is it 3? 3 x-intercepts. So those are 3 factors of the function. All right, I have -1, so x minus a -1, which is x plus 1. I have 1, so that's going to be x minus 1. And I have 2, which is x minus 2. So I have x plus 1 times x minus 1 times x minus 2. All right. Now we're going to look at multiplicity of those zeros. What's the multiplicity of -1? Does it touch or pass through? Does it touch or pass through? Does it touch or pass through? That tells you whether the degree is even or odd. If it touches, it's even. If it passes through, it's odd. And we always go with the smallest numbers because they want to use the smallest degree possible. So it just touches here. So the exponent on x plus 1 is going to be an even number. And the smallest even number that is positive is 2. Here it passes through. So that means it's going to have an odd multiplicity. And the smallest odd number, the smallest odd integer that's positive is 1. So its exponent is 1. Same thing with the 2. So the only thing missing here is what is a? So now I have f of x equals that. Now, something that's very important is to find out what a is, because we want to write the polynomial function, not just a generic form of it, where this could be the equation, or it could not, or it might not be. It all depends upon what a is. So this is basically a family of functions that have different leading coefficients. So I know a point on that line where x is 0 because putting 0 in for x is easy. So that means f of x equals 4, and that's going to be a times 0 plus 1 squared times 0 minus 1 times 0 minus 2. So I figure out what all these are, multiply them, and that's what the coefficient of a is, right? 0 plus 1 is 1. 1 squared is 1. So that's going to be 1 times a times 0 minus 1 is a negative 1. 0 minus 2 is a negative 2. So negative 2 times negative 1 is a positive 2. 2 times 1 is 2. So this is 2a equals 4, or a is 2. So I replace this a with a 2. So that means my function is f of x equals 2 times x plus 1 squared times x minus 1 times x minus 2. Now, I don't know if they multiply it all out. So we'll see. Okay, so they have those factors. All right, we have 2 zeros at x equals negative 1. So that means we have 1, 2, 3 turning points. So the smallest degree here is to the degree 4. If I add the exponents together, they equal 4, which matches what we discovered about turning points. There are 3 turning points, so the degree must be at least 4. The graph touches at x equals 1, so negative 1 has an even multiplicity. And the graph crosses at 2 and 1, so 1 and 2 have odd multiplicities. And since we're dealing with this, we want the smallest, so we go with the smallest numbers there. 1 for the odd multiplicities and 2 for the even multiplicities, which gives us this function here. All right, All that reminds us to find the leading coefficient A. From the figure, we know the 0.04 must lie on the graph, so you put 0 in for x and 4 in for the f of x. And you get A is 2. And so there you have it. Now you can multiply it out so it looks like a polynomial. And then use a graphing calculator to verify the result. And I won't ask you to do that. Now, the real zeros of a polynomial function. We're going to talk about the remainder and the remainder theorem and the factor theorem. The remainder theorem tells us that if you divide, if you use synthetic division, the remainder is if R is a factor, then F, no, that's the factor theorem. The remainder theorem is that well, we'll get into that. And there's no easy way, just short and sweet to say it. It'll just be more confusing. Okay. And then we'll use Descartes' rule of signs to determine the number of positive and the number of negative real zeros of a polynomial function. This does not directly help us find what those zeros are, but it gives us a starting point, or it gives us an idea if we're headed in the right direction. So if I find out we have positive, we definitely have a positive 0, then I can start looking for that positive one and find the negative ones a little later. Or if I know there's a negative one, then I can find, there's several different ways of dealing with it. And then we can use a rational zero theorem to list the potential rational zeros of a polynomial function. This is an easy process, but it can get, it can be a little confusing because of what you're doing. You end up dividing numbers. And so that's such an anathema for some people that it really throws them for a loop. But if you have a rational zero, this rational zero theorem will give you a set of numbers that that zero will come from. And then finding the real zeros of a polynomial function, so that's just not the rationals, but all of them. Solving polynomial equations, well, we do that while finding zeros. And then use the theorem for bounds on zero. This isn't, well, it's not very useful for our purposes, but it does help us in some ways. It tells us what the smallest y value can be, or the smallest x value and the largest x value. So we bound us between two x values. And yeah. And then use the intermediate value theorem. First of all, we're going to talk about what the intermediate value theorem is and how to use it. The intermediate value theorem is a very important theorem in mathematics. We use it in calculus and beyond. So it's an important theorem. Basically what it says, if you have two numbers for x where you have a sign change, then that means you have to have a zero between those two numbers. If it's a polynomial function or you have a smooth, continuous graph of a function, then if you have f of a is less than 0 and f of b is above 0, then between a and b you will have a 0 where it equals 0. At least one. You could have more than one. And I'm going to leave it there because we're at time. So there. Hi, bye. If you, I'll hang around if people have questions. If you don't have any questions, you're free to go.
What are your hours for? I don't know if you have a tutoring session or something like that.
On Monday, Wednesdays, it's I have an hour in the afternoon, like 3 to 4, and then on Tuesday, Thursdays, it's from 10 to 1:30. I mean 11 to 1:30.
What days do you say?
Tuesday, Thursday.
On Thursday.
Yeah.
11:30 to 1.
Well, 11 to 1:30. I have a 2 o'clock class, and I have a class that lets out at 10:10, and so I give myself 50 minutes to eat lunch.
Okay, thank you, sir.
Okay. All right, I'm gonna go ahead and end the Zoom. So unless you have questions for me, it's bye-bye time. And I'll see you all on Wednesday. Okay, bye.